Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
Hello, I'm here to introduce Mehrdad Mahjoubi. He's a MSR intern working with us at the Embedded Systems Group, working on FPGA verification and debugging. Let's see what he has to say.
Hello, everyone. Thanks for coming. I'm going to give like a 25 minutes presentation, and then afterwards I'll give you a quick demo of the tool that I have developed during my internship. It's not complete yet, but I can show the pieces to you, and you're hoping to get this tool in hands of designers pretty soon, so Neil and Ken and everybody in the group can start using it in the real designs. So as the title say, we have developed an automated FPGA design verification and debugging platform. So what it means is we are using FPGA for debugging hardware design in an earlier stage in whatever it is. It's an ASIC design or so on. So it's actually hardware emulation and verification on that platform. So here's a very quick outline of the talk. I'm going to give you the motivation for the work and tell you what is out there right now, what are the designers are using, and the industry is using, the state of the art. And I'll give a very quick background on assertion-based verification. And then afterwards, start talking about what we have, the automated debugging and the pieces of the tool. And after that, a demo of each of these stages and future work. And at the end, I'll conclude the talk. Okay. Anyone who has done hardware design can really correlate to these images here. You know, they may not have the money to destroy the computers, but they really wish they could. You know, so whenever you're doing hardware design, at the end of the day, nothing's going to work for you. So you have to look for bugs, and you have no idea where they're coming from. And to do verification and debugging, you have to verify the correctness of your design. So verification and debugging is everywhere, in software, hardware, whatever you want to do. But what makes hardware verification particularly different is the lack of consistency in the structure of design. So if you're designing an encryption core, another person is designing a microcontroller, another person is. So these are completely different designs. So if I can give you a recipe for that design, that's not going to work for you for another designer doing another kind of design. So the lack of consistent structure, architecture in hardware design makes it completely different from software design, where you're dealing with a fixed CPU architecture and you have a compiler and everything is almost the same for all software designers. So the lack of one-fits-all solution is a big deal. And the second problem is the lack of observability and controllability in hardware design. So it's very difficult to know a value of a certain net in your design at a given point in time unless you go inside the chip. You know, you hire some, I don't know, moving electron, go there and get this for me, come back, something like that. So you have to do probing, and you cannot see inside the chip unless you have, or you can simulate it on software, see what's happening in there. So also, there's a long recompile time usually for hardware design. So if you compare the design of the same size, it usually takes a longer time to recompile your design. So every time you find a bug, you fix it. You have to, like, I don't know, Neil does microcontroller design. He has to, like, wait a day, go home, come back next day. You know, it's not that bad. You take a day off, but so and in extreme hardware bugs can require total hardware replacement, especially if you're doing ASICs. So, so in practice, this is going to be a nightmare for industry. So Intel, that's a very famous example. You probably have seen this 100 times before, but it's worth re-mentioning that Intel has lost $500 million in its early stage Intel Pentium processor in '95, just for a bug in the floating point division instruction in their processor. And also interestingly, NASA lost $125 million over the Mars orbiter for an error in the software they had running on their unit. But here, the interesting observation is that the Mars orbiter cost less than what Intel lost in their Pentium processor. So NASA, not a big deal. Look at Pentium. Look at Intel. Yeah.
Yeah, but Intel did it again. We had the breach, NASA didn't.
Yeah, we're not, when you have that big of explosion, you
Take notice.
So anytime there is a bug in a processor, it delays the shipping of the product. You have to like spend so much time on finding that bug, and because of that, you may have to delay your product shipping. So once again, the lack of a standard and coherent approach and procedure in a hardware debugging, and also lack of tools and automation that can help you pinpoint the bugs and fix them. At the same time, complexity and large scale of the designs that designers are dealing with today are much different than the designs like 10 years ago, and it's growing, faster than before, has made it more challenging to find a little tiny bug in a very huge design. And insufficient computational power is also a problem, because if you could have simulated everything, then everything would have been fine. So there are actually some solutions out there, but a typical hardware designer does not really have access to those tools. There are very expensive hardware verification tools that Synopsys Mentor Graphics have for industry purposes, and nobody really knows how efficient those tools are. They cannot, and that there are proprietary languages across these tools. There is no consistent contrast and judgment in between those tools. Okay, so in a nutshell, you can divide the methodology that is being used in the state-of-the-art in three parts. And the first approach is using simulation to find bugs in your design. So that requires writing test benches. Certain test benches can be also self-checking, transaction-based test benches, giving lots of input vectors to your design and looking at the output. So the second approach is to use logic analyzer, integrated logic analyzer inside your chip, and to monitor signals and see what is going on. And the last category is formal methods. Formal methods use formal mathematics to check your formal description of your system versus what you have designed, and will do that for you. So the problem with formal mathematics is still, it's a very complex problem, and it might be computationally infeasible in certain cases. So also there are hybrid solutions in here. So you can mix simulation with formal methods and hardware. And any kind of hybrid solution here is possible, simulation-based and hardware-based. So ideally, you can divide your verification problem into subsets and use simulation hardware verification formal methods for each part of those things. So the tool that we are dealing with here is using hardware-based and simulation-based, and in the future we might be able to add certain formal methods into the tool to make it a more efficient tool. So now a few words on assertion-based verification. So on the previous slides, I talked about 3 methodology to find bugs there. But a systematic way to find and verify your design is to write models and describe conditions in your circuit, and then check and verify the correctness of what you have described using those tools on the previous slide. So I can write a few conditions, assertions, properties for my design, and then verify the correctness of those using simulation, using hardware, or using formal methods. So it's more like encapsulating properties and then verifying those things. So naturally, I think in your mind, everybody is going through that process, but it's more like a formal thing. I have this thing in my mind, let's go and check it. But here in assertion-based, you have to write things down in a formal way, using linear time logic, using conditional statements, and any kind of logic that you can write down on a piece of paper and then check it, instead of running things in your mind. So it has a potential of finding the bugs early in the RTL level design, and then detect them earlier than before. So I'm going to throw out there the goal of the project, what we are looking at the end, what we are trying to achieve throughout this project, and then this is more like the user experience kind of thing. So I, as a designer, would like to give the tool, my Verilog files, my hardware description language codes, HDL codes that are written to the tool, write down the assertions on a piece of paper, or maybe if I'm lazy, I just don't write those assertions. It's optional. I just give the computer to my designs, and I tell, okay, tell me what's wrong with my design, right? That's very high level. Give computer the design, and computer just tells me, okay, I think your design is not working. There is something wrong. This is the ideal case for a designer. So how can we get close to that? Probably it's too sci-fi to really have that, but we can get slightly close to that. So given a design, the computer can learn its behavior. So assuming that bugs happen once in a blue moon, but they happen, but not so often that you can see them, you can detect those outlier behavior. So it's like a machine learning approach. You want to find inconsistent behavior in simulation traces, in hardware traces. So now the assumption is that if bugs happen once in a blue moon, not so often, you have a good chance to learn the good behavior and isolate the buggy and bad behavior. So the process is that extract, and we use the term mine, which is a established term in the community, to mine assertions from your design. So it's assertion mining, it's specification mining. So after you've mined these assertions, you can pass it through the designer, say, okay, I have mined these things. Some of them are very trivial assertions. Some of them are more complex. Tell me if these are good. And say, okay, good. Move on. So after you have gotten these assertions, you have to check them versus your design. You can do that in simulation, but it's very slow. So we are looking into faster approach. So we can take these assertions, synthesize them into state machines. So I would call it PSL to Verilog. PSL is a property specification language which is becoming a standard. So you synthesize your assertions, and you merge those assertions with the ones that the designer have or might have provided. So, and then you implement those assertions onto the hardware, and you let it run. Run for a day, run for 5 minutes, until something fails. And then you have an interface that tells you, at this clock cycle, this assertion failed. And then through software, you have the ability to set certain parameters to your assertions. So you would like to avoid the recompile time of your hardware. So you can, I will show how this can be achieved, but you can set certain parameters in your assertions through software without having to recompile things. So think of parametric assertions. So you have parametric assertions that you set those parameters through software. And then you would like to maintain least impact on the original design. So as you're adding all these debugging peripherals to your main circuit, you don't want to change the functionality of the main circuit as you're adding things around it or inside it. So I show what that really means. Okay. Yeah.
When you get an assertion, what do you do?
We check for we check for its correctness.
Okay. Check for the correctness of the assertion.
Of the assertion. So the assertions can come in any kind of a logic statement, but the kind of statements that are common now are linear time logic. So an example would be, if this event happens, it has to stay valid until the other event happens. Or the whole thing, the whole statement, eventually something else should happen. So instead of eventually, until, next, alternating patterns, and so on, will form certain things that you might observe in your design. So you express those assertions in a given standard logic, and then you pass it on to the tool. So, okay, back to the spec mining. As I said before, it's originally the designer's task to write down the assertions. But since it's first of all, it's a tedious process. If you work in I haven't worked in a verification department in Intel, but I have friends that have told me they give you a code, there are no assertions to check. The designer left, quit his job, he didn't write the assertion, and so on. So you have to go through the whole cycle, and the pay was not enough. He didn't write the assertions, stuff like that. So it's originally the designer's task to write the assertions, but because of all these issues, there are lack of assertions that give you a complete coverage of the correctness of your circuit. So one alternative approach is to hire a laptop to write the assertions for you. And here I have to emphasize that the assumption is that the design is acting is acting correctly most of the time. So what happens if the traces, if you get a false positive, if the tool tells you there is a bug there, and you go and dig there and there was no bug, it's okay. You just wasted, a couple of hours for something that was not an issue. But if the tool tells you there was no bug, let's keep going, and then you tape out your, CPU comes back, and you lost a couple of millions of dollars. So false negatives are not okay. So that should be set to almost 0. But you can tolerate false positive based on how patient you are. Okay, so this is actually a work Wenkao, a previous intern at MSR has done is to. So the tool is that you run a benchmark on your circuit and you collect the output traces through a simulation tool, Model Sim. You get a VCD dump which is your simulation traces. You pass these simulation traces to the spec mine, and then the spec mining engine looks for patterns, alternating patterns, next patterns, until patterns, and eventual patterns. So you also provide the pattern library to the tool. So look for these patterns in the traces and tell me when they happen. And after it has mined this pattern, it performs a reduction on the patterns because sometimes the patterns are redundant. You want to remove the redundant ones. Also, the chaining of the patterns or merging of the pattern to get more efficient assertions. And at the end, it ranks the assertions based on how often they happened or they were observed in the traces. So, but this is like an unsupervised learning. Remember when I was explaining the formal methods, how we can use formal methods? This is where we can use formal methods. After you get these assertions, if you have a tool that tells you this is an important assertion because it gives you very good coverage on a lot of different action, then we pick that. So the kind of ranking and reduction that we have are kind of, we are trying to reduce the number. But if there is an engine that tells you this is a really important assertion because it gives you a lot of coverage, that's formal methods. It can mathematically verify for you that this is an important assertion because of that coverage. We keep it. So the missing part is to apply formal methods to the output of this tool to get the more important assertions based on the coverage, not based on how often they appear in the output traces. Okay, now after you get these assertions, you have to map them, synthesize them to a state machine. So this is still a challenging problem because you might end up in a state explosion state. So you want to efficiently map this logic statement into a state machine and with minimal number of states because you don't want to use a lot of hardware. So in a paper in 2005, this problem was tackled in a very efficient way. And so the trick is to rewrite properties. So you have a logic and say, this logic changes if I have this input. So for example, say your logic is that if I move to the city, my life would be wonderful. But if somebody gives you an input, your logic might change, right? Something like that. So it's, say, logic P can be rewritten to P5 if the input is this one. And so it keeps writing the logics until they reappear in the chain. So P1 reappears again here, again here. So the assumption is that you are going inside a loop in the state machine. So, and then it wraps up this chain into a state machine by observing how you're traversing in the state machine. Okay, so now we have two parts: mining the specs, synthesizing them. Now, the next step is to insert them into the design. What is missing there is how to automatically attach the probes into the signals that you want to monitor. So this part of the tool we call a probe insertion. So given the names of the nets, first the probe insertion tool parses the Verilog design, the input that you provide to the tool, and then it detects a system, the modular hierarchy of your design, and then modifies the module declaration, the module instantiation, adds extra ports to them. So you can, for example, add a wire from this leaf node and route it to the top node so you can have an interface, debug interface in your system. So instead of you going through your code, writing those wires and bringing them down, the tool will take care of that for you. Okay, now that we inserted the core into the design, we would like to see what kind of things the interface we would like, what kind of information we would like to see from the interface. So it's more like a user experience kind of thing. So right now the tool will do these things. You provide in the software, without recompiling, if you have a software interface, you say, I want to enable these sets of assertions. Say you have 1,000 assertions, but you don't want to check them all the time. Say, okay, I just want to check assertion 1, 2, X, and so on. So you enable those assertions that you want to check, and then you can set the parameters for your assertion. So think of the notion of parametric assertion. So, and then you set the scope time, scope window time. So certain assertions have to be frequently checked. Think of an eventually logic. I will eventually finish this work. This logic will have no meaning if there is no time scope there, right? Eventually logic will have no meaning if there is no time definition, right? I will finish the PowerPoint slides by tomorrow, right? If there is no tomorrow, it's meaningless, right? So you set the scope time for certain assertions that make sense. For example, if the next assertion, if this happened, next this should happen, then the scope time doesn't really matter because next is we have a clock, and after that something should happen. So, and we have a method to set the clock frequency in hardware through software. Okay, I think Ken.
Why would you turn off any of the assertions?
Because sometimes you write wrong assertions. And then you realize I wrote the wrong assertion and it was my fault. So I don't want to go into the tool, delete it, recompile everything. Just ignore that assertion. Or I understand this is a trivial bug. I don't care about. I don't know. It gives you the flexibility to not to recompile everything, still not caring about certain assertions.
So you can collect multiple bugs. So it's like, okay, I know about that bug already.
Right.
Stop.
Exactly.
Bolting on that.
Exactly. And also the tool stops everything as soon as it observes the first failure in the assertion. So abort, go to the software, send all these diagnostic information, halt everything. So, and also as you said, you can say, okay, keep going, don't check this assertion, and so on.
I was just going to ask, what's the benefit of doing all this in hardware? It just seems like you're making your life
It's
harder.
way much faster. It's a very good question. So if you want to do the same kind of thing in the software, it's going to take at least 3 orders of magnitude more time. So it's like 1,000x slower in software. So if you have a larger design.
Well, it just seems like if you're really wanted to work correctly, you would build a formal model for it. You would use a language that had kind of something like Estrel or something that was really sound for building very like it's verified when you write it and it's very stringent to when it checks it and things like that. It just seems like if you were to have this much care about every single small little bug, you would kind of follow that flow.
Well, ideally, writing formal methods is the way to go. But some of the problems are computationally intractable with the kind of hardware that we have. So if you run those proofs on a computer, it might take much longer than this.
For that that you put everything in simulation.
Right,
So
right.
if you're
And I guess if the
interacting-
hardware already existed too, if you already had Verilog.
Yeah, well, so if you're interacting with a flash device, right, so how do you simulate that?
Sure.
That
Right,
and,
exactly. So
you know, I have a bad habit of being lazy, so don't do it.
Right, right, right. I guess it's true.
And yeah, it's actually a very good point. So you can, instead of writing test benches, we have the input buffer and output buffer in the interface. So you can send the data to whatever computation you want to do, get back the data, do the, and then compare, do the same kind of computation in software. It's more like a co-hardware software simulation, and then you contrast the result you get from software. So you're at the same time sending the data, the circuit is running at speed, and you're checking its functionality and correctness at the same time. And as Ken mentioned, sometimes it's difficult to simulate Ethernet controller in software. You have to write it down and so on. But
I think I was just confused. It seemed like you were just basically trying to do all debugging in hardware. That's what it seemed like. And that just seems silly. It takes forever. I mean, you should do debugging first, not in hardware, as much as you can, right? I mean, you don't want to just write Verilog and throw it on FPGA and plug some stuff in and say, I got like 1,000 insertions.
right.
So that's kind of what I thought you were saying, but I see what you mean now.
Well, yeah. I mean, when you get to this point, you have to make sure that your design is sane, but sometimes it goes crazy. But you're trying to find what's going on. Sometimes, not all the time. So it's not like I write a totally crappy code. I don't know what it does. I want the tool to redesign it for me, something like that. So its assumption is that you have a good code. You can't find the bugs there. Something's going on. You're trying to achieve that.
Actually, I have a follow-up question then. So this tool, so you'd actually use this to find bugs that you saw in simulation, but you couldn't. They were basically hard to. It just took a while to find them, or.
Okay,
or would
so
you actually use this tool to
the
find
real world
bugs that don't
scenario
exist?
would be I have an AES core, and I give these input blocks to the core. I get the encryption or decryption of the input, and then I compare it with what values I expect to see. It runs, and at some cycle, the values do not match. There is something wrong. Or you're running some instruction on a CPU. It's running at certain for certain instructions or data input data, something fails. So you're not doing that in the simulation. It's running on the hardware, but something fails there. So you can still catch it without having to do simulation. You're looking at that. So okay, so if you want to go and look at what's happening locally, we have that feature which is, okay, this assertion failed, roll back in time, repeat the same operation, but this time capture everything from X number of clock cycle before, store it in a chip scope logic analyzer, integrated logic analyzer. Now look at it this time with the chip scope. So the tool has that ability to show you the waveforms also, so you don't have to deal with the simulation.
In other cases, again, we didn't provide timing specifications, so we're
Right,
trying
right.
simulation, and it doesn't work in reality.
Well, right.
Well, for that matter, it's a matter of input vector coverage, right? So, in a reasonable amount of time, how many test vectors do you feed this thing in simulation?
Yeah, I mean, I guess that's why I was asking. I mean, you want to simulate it first, right? That's to some extent.
Well, that's kind of what the specification finding comes in. You've simulated it
Right.
first.
So you're like,
It
this
seems
kind of
right.
works. It seems pretty good, but let's run it through this, and then this is kind of a runtime thing.
Right, and it's also allows you to get more coverage over more time, and there's also the objects you can't account for
Exactly, yeah.
in simulation, like your interface to DDR2. Well, that's kind of hard to simulate
Sure.
or to come at flash.
Right.
Okay, so
I still have a question. It's very clear about the figure.
you were not clear about it.
That figure, you have the output buffer and you have the chip scope. So what's the different?
So this is like an Ethernet controller that Ken has developed, and you can communicate with with the on-chip device through Ethernet controller. So, so everything in that blue box is an API control for that.
So why you still need a chip scope if you have an assertion already into the FSM?
Well, the input buffer and output buffer are for communicating with the device under test. So you give it, so they're not for diagnostic information.
Oh, okay.
So ChipScope Pro give you diagnostic information on certain signals that you want to probe, but for input buffer and output buffer, you're just sending data and getting back. You're just running the circuit. So I get back to this figure in a minute too. Okay, so there are also timing issues that you may miss in simulation. Your circuit might work functionally correct, but considering the timing, it may fail, right? So simulating for timing dependent design is also an issue. So you might have race conditions. You may have forgotten to write timing constraints in certain paths, especially when you're dealing with multi-clock domains. And a very scary thing is that you might have something that happens post-silicon after you implement things. You might be having to deal with delay variation defects on delays and such. It's not so common, but you're going to see more of these. So to check for timing issues, we have added this feature to the tool that gives you the ability to tune the hardware clock on the fly in hardware. So the clock is running at 100 megahertz, and I say, okay, increase the frequency to 101 megahertz. It's okay, increase it one step, 102 megahertz. So without having to resynthesize everything in the code, we tune the hardware clock using the PLL phase lock loops in the FPGA. So as a designer, you provide a target frequency, and then we have a tool that searches for optimal phase lock loop attribute settings. So each phase lock loop here has a D attribute, which is a division attribute, M multiplication, and O is also a division. So these three here. But there are certain constraints. So it's a search problem. You have to look for the best setting for these attributes. For example, the input to the phase detector, phase frequency detector, cannot be higher than a certain frequency. The output of the VCO cannot be lower than a certain frequency, higher than a certain frequency. So considering all these constraints, we have this algorithm that looks for an optimal PLL setting given an input frequency. And after finding these coefficients, the PLL is to be reconfigured with the new attributes. So the figure on top shows if you have one PLL, and if you all possible frequencies you can synthesize with a single PLL on a Vertex 5 device, all sorted out. So they are sorted from 0, like about 3 megahertz to 600 megahertz, 700 megahertz. You see there are more points here. There are more number of frequencies you can synthesize in lower frequencies than higher frequency. So it's kind of sparse. Think of it as a histogram. So higher frequencies, it's more difficult to synthesize higher frequencies with higher precision. So they're kind of sparse.
So basically I have to read the frequency in reverse. I want 400, how do I get 400? Can I qualify?
Right. So the thing is that if you need a low frequency, probably one PLL would be enough. But if you want an accurate high frequency, there's a chance that you don't hit that frequency in the upper curve. So you need a second PLL for that. So I will show you.
What is frequency count?
So you can synthesize about 11 distinct frequencies with one PLL.
Okay.
So now,
bottom of the graph is frequency count.
Yeah, I mean, this is the number of distinct frequencies you can synthesize with one PLL.
So it's based
It's just sort. It's a vector.
Oh, I see.
You sort the
see.
vector of all possible
I see.
frequencies that you can synthesize.
Is that based on your different setting of the DMO?
What is that?
DMO.
Right.
Based on different setting, you get this number.
Right. Each point on this curve corresponds to a different DMO setting. But they're feasible settings. There are certain settings that are not feasible. There are certain settings that produce duplicate frequencies. For example, if you multiply both D and M by 2, you get the same frequency because one of them is on the denominator, the other is on the numerator. So there are lots of redundancies. So these are like the best frequencies you.
What do you mean, like if you cannot get high frequency in the second PLL?
Right.
What that means?
So with 2 PLL, you can synthesize a lot more frequencies than with 1 PLL because you have three degrees of freedom here, 3 parameters to play with. With 2 PLL, you have 6 sets of parameters. So the chances you hit a closer frequency is higher.
So I guess it'd be nice to have a picture that says with 2 PLLs and with 3 PLLs.
Right.
There's a variable in here that's not taking into account, and that's the input clock.
Okay,
So
you're right.
so-
Input
so
clock.
could just
I
take
assume the board.
crystal that I put in-
What is that?
There's a crystal socket
Right.
on most boards, and I can just take that out and put in a different crystal.
And then you have
Right.
new-
I did the simulation with the onboard clock, 100 megahertz onboard clock. So you're right. This diagram changes if you have a different input frequency. That is the case for the second PLL because the second PLL takes a different input frequency from the first PLL. So if you don't want to get a second, if you don't want to get a crystal oscillator, you can do 2 PLL, and most surely you can hit the frequency that you desire. Okay. So you're kind of running out of time. So guided placements. What is the problem here? So assume you have a modular design. You have a microcontroller, encryption core, some other peripherals. And you want to debug only one module in that design. So you want to take out a module from a bigger design and debug that. So the problem is that if you take it out and put it next to a bunch of debugging interfaces, things might change. So you want to have least impact when you're moving that thing out of the design and put it into a new design with a different setting so it retains the same behavior. So the trick is to have a consistent behavior. So to achieve that, we run the original design with no debugging peripherals and no debugging interfaces, anything. Just original design. And then we extract the placement of the certain module that you want to debug. And then we pass it on to the debugging tool. The next time you're doing debugging, it enforces the placement of that certain module so you get a consistent behavior. Xilinx has a smart guide technology, and it's supposed to achieve the same goals, but it only works on if you're doing very small incremental changes on your design. So I have a comparison of the performance here. Okay. So one example, I have, I'm assuming I'm debugging a multiplier, which is attached to the Ethernet communication interface. So I add one verification unit or 3 verification units, and the 3 top figures I am enforcing the placement to follow the behavior when there is no verification unit. And the bottom figure, I'm not enforcing constraints. So you see, visually, the placement is retaining its shape, but in the bottom, when there are no placement constraints extracted from this design, the top left design, then it does a completely different placement. So, and then at the bottom, I'm comparing the the cost you're paying for performance as you're enforcing those placements. Because the tool wants to do the best placement that gives you the least power consumption or the least timing, the best timing. But once you enforce the placement, you are kind of constraining that optimization problem. So you naturally get a lower performance. But that's very small here, not negligible. I mean, that's negligible. And the problem is not really losing performance, because in the original design, you're getting the same placement and nothing's changing. You're losing performance compared to the case that there are no other peripherals and you let the tool do the placement for you, and there's no other modules around your module. Okay, this is a better visualization. Okay, so we have a standalone AES core, just an AES core that's placed like that. And then we add the communication interface and the debugging interface to that. And here, I explained to you why this happens, and I have a correction for that. Here we are enforcing the placement constraint. So we would like the red region to be exactly like here, while everything else is placed around that. So if you look at this area, we get there is a shadow in that red region. Oops, sorry. There is a shadow right there. So the problem is that whenever you re-implement and you re-synthesize your design, the name of the components might change. The tool has a random number generator that for certain memory components, it assigns a new name every time you do recompile. So the names of certain components here change, and I tell the tool, okay, lock this component at this location. And the tool tells me there is no such a component. So if you see, these components are being locked because their names haven't changed. But the ones whose names have changed, they're not locked down, and they're placed scattered all around the place. So I tell you a solution for that. So using a smart guide, not much similarity in the placement. No constraint, it's moved to another place. So, okay, these two figures are the same as before to the left. Now I did a trick, and I say, okay, the names of these components are changing, but the rectangle around this are not changing. I extract the rectangle, and I enforce the rectangular area around instead of each component. And you can do both. You can do, so this component's name's changing, but the rectangular area is not changing. So combining these two, you can get a pretty close placement of the same module.
So the whole point of doing all this is so that you don't have your debug stuff interfere with your original stuff.
Right.
You don't want the synthesis tools to replace it and then introduce new bugs.
Right, exactly. Okay, so the communication interface that we're using is CERT Ethernet, designed by Ken. It's a very handy interface. You have a bunch of C files. That there's the software interface and Verilog files, and the probe insertion. Most of the tools are Python based. Most of the parts. The Verilog parsing is being done with the PyParsing package. PSO to Verilog uses a Ply, Python, Lex, Yawk parser, and then we have an XDL to PCF. PCF is a physical constraint file, which is equivalent of UCF, but it's for after implementation, after mapping, before doing place and route. But UCF is in the synthesis and in mapping. Okay, we're back into the flow diagram. It's the tool flow, how things work, just to wrap everything up. So we have the original design simulated, get the output traces. Mining the specs from the original design, and then also we provide the user specs. Then these are being synthesized to state machines. And at the same time, we extract the probing information, insert the probing into the original design, and we implement the hardware assertion checker core with the insert the probe, enforcing the constraint we have from the previous round we've collected from before, and then we do the debugging through the circuit interface. Okay, I'm going to give a quick demo on the interface for you. I'm debugging this for an example. In AS core, we've added a bunch of PSL assertions, and I demonstrate a debugging scenario, and also I run the spec mine tool for you in the placement extraction, and I show you how PL attributes are being generated for a given frequency. So let's move on to those things. Before I finish, I want to thank my mentor, Neil Pittman, for his support, and I had a really good time here, and Sandro for his wise showing the way through the project, and also we have used a lot of work from previous interns. This is actually joint work with Kenneth Macmillan and Vinkal Lee. So I'm remoting to remoting to my desktop. I have an FPGA board. I have to visualize this for you. I couldn't bring everything. It would have been made a better impression if I had like hardware running here, but so I have the hardware running on my desk connected to my computer, and this is the project that I have here. Okay, so we are debugging an AS core, and I have these sets of assertions here written in PSL language. So this is an example of how you can write assertions in PSL. So it starts with defining the atomic expressions. The atomic expressions evaluate to 0 or 1 at any time instant. So this is saying that the atomic expression W0 equals to this. Whenever I send a command request, eventually it has to be acknowledged. So it's more like a transaction level assertion. Every request has to be eventually acknowledged within a time window that I define in the software. I'll show you that time window too. The second one says if in the AS core, I read 48 bytes and then decrypt or encrypt those 48 bytes, and then I spit out 48 bytes. So this says wait after you have read 48 bytes. So this says after AES count equals 48, wait command. This is the next thing that should happen. You have to wait. The wait command has to be issued. So this is another assertion. So the next one says AES in data valid has to stay high until you have read 48 bytes. So it shouldn't go down if you haven't finished reading those things. So this is like an until assertion. W1 has to stay high until W2 goes high. So this also has a notion of time, because until in an until event there's a notion of time. The assertion can fail before the time has expired, but it may wait until the end of it too. So in the next assertion, there is no notion of time. again, we have another next assertion which says if the FIFO is full, do not. The next thing should happen is that stop requesting things. These are more like transaction level assertions. The next one is if I start reading the data, the core has to finally spit out something. You can't just keep reading things and not give an output. So it's like if the data invalid is 1, eventually the data out should be valid. So again, another eventually. So you can write more complex PSL properties. This is just for the sake of demonstration. It can be a chain of different kind of logic. So you can have eventually this event chained by some other thing. So this is very simple assertions that I wrote for demonstrating. So giving these assertions to the tool that I show, that I will show, the tool spits out the state machine for you. So this is the state machine that I get from after synthesis. And then the state machine is connected to the signals that I'm probing for monitoring their behavior into the tool. Okay. So now this is the software side. So I have already programmed the FPGAs running the code. So when I run this thing, bad news. Okay, I think I'm running an outdated version here. Okay. Okay, I see what's wrong. Okay, I'm going to disable all the verification units in the code. So vunit enable 0, everything is disabled. Oh, sorry. Okay. So this says assertion 0 was violated at clock cycle 0. Makes sense. Nothing is being checked. And now I'm going to check assertion 16. Assertion, this is binary coded, the last assertion. Assertion 5. Okay, assertion 16 was violated at clock cycle 23. So, what is assertion? Oh, okay, 16 is like 1, 0, 0, 0, 0. It's like a binary coded. The last assertion is being violated at clock 23. What was the last assertion? The assertion was that if the data is valid, eventually the tool has to spit out something. Eventually has a time scope, right? A time notion. How long am I waiting? What is the scope set here? It's set to 20. So I wait 20 clock cycle. I repeat checking that assertion every 20 clock cycle. Maybe that time is not enough for the AES core to process that data. Let me increase that to, say, 22, 25. Sorry. It is still failing. Was violated clock cycle 28, but it's still. I added 5 more clock cycle. It was 23. Now it's 25, 28. So let me do 100. I'm gonna wait 100 clock cycle. Okay, it didn't fail this time. Say assertion 0 was. So it's like I'm changing the time and scope and then checking if that assertion failed or not. So I can do the same thing with other assertions here. Also, I was talking about parametric assertions. Let's see. Here, if there are certain ways you can parameterize your assertion. For example, I can pass on the value 48 from software to the assertion. So I don't have to resynthesize these assertions every time I want to change these parameters. So in certain cases, you can parameterize assertions. So you can pass on these values to the assertions to the software. So you can add more flexibility to the tool. Okay, let me show you the PLO thing real quick. Okay, somebody tells me a frequency they would like to synthesize something between 3 to 600 with any precision, 600 megahertz. I'm going to put it in there. Okay, you can be more accurate. Sorry. Target clock frequency. My software interface is still. I'm looking for. Okay, what was that frequency? 173.1234. Okay. 7. Okay.
That's megahertz or that's
megahertz? Okay. It takes a little while because. Okay, we have too many options here. So. Okay. Okay. So the first setting, the second PLO outputs a frequency of 173.125. 123, we've got 123 here. So with this one, output frequency equals 123. The settings are for the second PLO M97D103, and for the second PLO, for the first PLO, M34D500127. So I'm printing out things with low precision. Probably you got that 7247, but it's not because I'm using cout in the printing without formatting the string. You're not seeing that thing. But so it gives you a list of frequencies that are within a given tolerance window. I've specified that, and then you can choose the closest and so on. Okay. Well, no, yeah. So the tool is still not able to do dynamic reconfiguration. This is the next thing we want to do. After you get these numbers, you send it to FPGA, and then you reconfigure those to PLOs, and then you can get those kind of timing information from the device too.
So at the moment, it's just.
I'm just generating the coefficients. Yeah. The problem with the Vertex 5 is that the information to do dynamic port reconfiguration of the PLL is not well documented, but that information exists for Vertex 6. So, yeah, that part is still on the way. So, what else we have? Okay, spec mine. Let's go to spec mine. Mining a specification from debugger. I think I had it open. Okay, so this is how you run the spec mine. So you give it a VCD dump, and then it outputs the specs for you. So I'm gonna run this here. The VCD is the output you get from simulation tools, usually Model Sim. It stands for vector charge dump. No. Yeah. Okay, so these are the two files. I gave it AES that I got from running Model Sim, and then the specs. Let's look at the specs. Okay, so this says the number of patterns before merging. The number of events, 31. The length of traces, 3,000 something. The number of patterns after merging, after chaining. So this is one pattern. This A stands for alternating pattern. So this pattern alternates. So we have every time the address is 5, next you have 6. So we have this 5, 6 in alternation. So whenever you have 5, you have 7. 5, you have 8. So the tool is basically saying this address is incrementing in a verbose way. So that's how the model formal methods can come handy. They can look at these things and say, okay, they're all saying the same thing mathematically, right? So I can do another reduction on this. The downside is that if you want to directly synthesize these assertions, you're going to have a lot of redundancy in hardware. So if you had unlimited space, then that wouldn't be any problem. So what is F is eventually. So this says address equal 4 and address equal 4. If this happened, eventually address equal 3, address equal 3 should happen. So these are like eventually patterns, and so on. So they're written in linear, the same kind of thing, linear time logic.
And this is constrained just by what you simulated too, though, right?
Right. So the longer you have traces,
very well have never been asserted. In a sense.
What is that?
Like, I mean, if it says, you know, you could not get an assertion. Like, so if yeah, you basically can't capture everything, right? I mean, you get some stuff, but you can't see. You don't get a lot of things too.
Yeah, the longer the simulation traces, right, the more, say, confidence you would have in your patterns, right, and you might probably get more meaningful patterns than running on short traces.
But that would never give you any false negatives, right? So it'll never give you a case where the assertion was actually not right, spec mining, right? Because there's always
you have lots of false negatives. You have no false positives.
Yeah, it's never going to say this is an assertion, but it's wrong, right? That the spec mining tool.
Right. It just gives you a bunch of assertions. That might not be a correct assertion. But that is a very dangerous thing. But it might happen.
Because isn't it just looking at the physical?
Or no, it's a false
things?
positive.
well, it's looking at the physical signals, right? Saying this is what this was, and then this is what it turned out to be, kind of thing, right? It's generating assertions from actually what happened, so you couldn't get anything that was wrong.
Wait, no, you can get both false positives and false.
Right. So if you have bugs in your traces, the learning is also done on the buggy traces. So you.
I see what you mean. Right. Yeah.
But we are
Right,
hoping
depending on the
it's
data
like
from the
the assumption
simulation.
is that those are not too often that affect the patterns. So you have something that happens frequently, then it affects your learning. You're learning the wrong behavior. It's like a kid.
Or it could be like, does the right thing 99% of the time, but 1% of the time does the wrong thing.
Right.
So trying to pull that out.
Right. So if your code was really bad, then you would be full of assertions that were totally wrong.
Right.
Okay.
That's why we say that you won't be somewhat confident if you go through simulators.
That's what I was
you're 99% right.
So it's not. It's really not just like code, push button, give me my assertions, and then I put this into hardware and you say push button, and you're gonna help me figure it out.
You're assuming that you're mostly there.
Yeah. Okay. That makes sense.
How much time do we have? Okay. Sure. One or two quick things, and we can wrap things up. So, so the other tool is the XDL to PCF. So after you do your design, Xilinx at the end of all the process, Xilinx spits out a file with the format XDL, which stands for Xilinx Description Language. So it's a closed language, but it's easy to understand. It has a very simple syntax, and it tells you, it's the net list of the FPGA, how things are being connected in the FPGA, how things are being placed. So, for example, I'm going to open up one XDL file here, show it to you. Okay, here it is. So this is, for example, for the AES core, the tool spits out this file, which this is like, for example, this says, this is an I/O buffer placed at, this location, and it's configured this way. This parameter is set to off, this parameter off, and so on. And it's also, the I/O standard is set to this very low-level net list of the FPGA. So what we are processing this for is to extract the placement of the components with given names. So the script takes this file as the input, and then outputs a PCF file. So the script is finished running. Open AES constraint PCF. So this is the PCF constraint file, which was generated from that. So it tells the tool to place this component at this site and so on. So you see these names? These are the things that change. They're being generated with a random number generator. So the rest, which look normal, this is, for example, a name that is not changing, but this one changes, and so on. Anyways, for the P2V, let me show the synthesis tool as well. Okay, so for P2V, we write the assertions here. So this is, for example, first assertion that we had there, AES byte counts 48, the same assertions that we had in the Xilinx tool that I showed. So okay. Okay, so we run this. Okay, so we say my P2V, run this, and then it synthesizes into AES underlying VUs. Go look at that. AES underlying VUs dot Verilog. So these are the state machines generated from these assertions. So currently, we have pieces of these tools running. We still need some work to put them all together, so we isolate the designer from having to deal with what's going on inside. As I said, the goal is you provide your design, and if you're really willing, you can write your own assertions. If not, the tool can mine it for you. And the rest is being taken care of, and then you sit in front of your computer and then you run on your interface and check the assertions that are there in the tool. The vision is that the tool also generates the C codes, parts of the C code that you can insert them as header file that that has the parameters set for those assertions and so on. So you don't have to even write those parts in the C code. So that would be the flow of the things that we have, and hopefully we get things together soon into something that people start using. Any question? All right, thanks a lot. I appreciate your time.